Hello everyone, welcome back to Physics 425. Last time we were talking about Bose-Einstein condensation, and in particular we were trying to come up with a way to define the critical temperature below which this condensation occurs. And so that expression we came up with is in the red box. So what I want to do today is I want to see if we can kind of develop a little bit of a different understanding of the condition for Bose-Einstein condensation, which might help to develop a little bit more intuition around this concept. To do that, what we're going to do is we're going to think about the space occupied by a single particle in a system of identical bosons. Okay, so delta X is going to represent the space occupied by a single particle in the system. So from the Heisenberg uncertainty principle, we know that we can't kind of pinpoint the exact position of a particle, and so what we're going to use to represent this space occupied by the particle is the spatial extent of the particle's wave function, or alternatively the de Broglie wavelength. So this de Broglie wavelength, lambda is 2 pi over k, where k is the magnitude of the wave vector. Okay, well, for a system of non-interacting bosons, we know that its energy is kinetic energy, which is h bar k, the momentum squared, divided by 2m. And if our system's at some temperature T, then the kinetic energy of the particles is going to be on order of kBt. And so if we use this, we can solve for k, which would be, let's see, our 1 over k would be h bar squared divided by 2m kBt, and then take the square root of all of that. Like so. And so that means that this de Broglie wavelength is on order of 2 pi h bar all squared divided by 2m kBt. All right, so for the purposes of this discussion, I'm not really going to worry about factors of 2 and pi, these small numerical values. We just want to do like an order of magnitude estimate. So let's drop all of those unnecessary factors. And so this is the one-dimensional space occupied by a single particle in the system. And one thing you can notice is that you can already see that it's inversely proportional to temperature, or the square root of temperature. So as you go down to lower and lower temperatures, the spatial extent of this particle's wave function is going to grow. And so that's going to be an important point for us. And so if we were talking about 3D, then the volume occupied by each particle is going to be the cube of this de Broglie wavelength. So the volume occupied per particle, or sometimes people refer to this as like a quantum volume, is delta x cubed is around the cube of this de Broglie wavelength, which is going to be, ignoring factors of 2 and pi, h bar squared m over kBt to the 3 halves. All right. Now we could also think about the space available per particle. So let's consider also the space available per particle in the system. Well, if our system has volume, let's say system of volume V. So if our system has the volume V and n particles, then the space available per particle is V over n, which is just 1 over the particle number density. Okay, and so we can think of two possible cases. So I'm going to draw this in 2D, but you can imagine that this is a 3D picture also coming out of the screen. And so we can start to partition our system, which has some total volume, into n equal volumes. And each of these squares, or in 3D, each of these cubes represents the space that's available to a particle. So for example, we could say, take one of these squares, and the size of that square is 1 over the number density. And so one case is to think about is the high temperature limit. High T, or this would be like a classical limit. Okay, so if we go to high temperatures, then this quantum volume, lambda cubed, becomes small because there's temperatures in the denominator. So at high temperatures, this quantum volume is small. And so maybe it's something like this. So over here is lambda cubed, which is proportional to 1 over t to the 3/2. And so at high temperature, that's a small amount. And so in this limit, the amount of space that's available for each particle is large compared to the spatial extent of the particle's wavelength. Okay. The other limit, of course, is the low temperature limit. And so I'll draw the same kind of grid here. If we keep our system volume the same size and we have the same number of particles, then the space available per particle doesn't change. So that's still the same. And so this is the 1 over n is here. But because the quantum volume grows as temperature decreases, we can reach a limit where this quantum volume becomes bigger than the space available per particle. And so this is lambda cubed. And so this is the low temperature or the quantum limit. So the low T or quantum limit. And so what happens is that there's this crossover where the spatial extent of the wavelength increases beyond the space available per particle, and that means that the wave functions of adjacent particles will start to overlap. So when the wave function of or wave functions of adjacent particles overlap, the quantum nature of the system becomes apparent on a macroscopic scale. And when that happens, you get new physical phenomena. And quite often, these phenomena are very unfamiliar to our common experience. And so, the obvious examples are superfluidity and superconductivity. But those aren't the only possibilities. So what happens when the wave functions of individual particles overlap is that the particles in a Bose-Einstein condensation behave as if belonging to a single macroscopic wave function. And this wave function extends, that extends throughout the entire volume of the system. And so we saw a case of this when we looked at the video of the liquid helium boiling at 4 Kelvin initially and then being cooled down by pumping on the vapor above the liquid, evaporative cooling. And when we reached about 2.2 or 2.17 Kelvin, the boiling suddenly stopped, and you could see a sudden change in the entire volume, which could be several liters of this liquid helium instantaneously. And so that's like a macroscopic quantum effect. So let's check this condition that the space available per particle is equal to the quantum volume. Well, what that means is that 1 over n would have to be equal to, let's see, lambda cubed was h bar squared over m kBt. So it was h bar squared over m kBt, and that was all to the 3/2 power. And so we'll call this T star, right? T star is the temperature. T star is the temperature at which 1 over n is equal to lambda cubed. Okay, and what we're going to try to do is compare that to the Tc that we calculated in the last video. Okay, so if we do some rearranging, let's see, h bar squared m over kb t star is going to be equal to 1 over n to the 2/3. And so therefore kb t star is around h bar squared m times n to the 2/3. And so we can compare to kBTC for the Bose-Einstein condensation, which was 3.31 h bar squared m times n to the 2/3. And so these are the same within numerical constants. These are the same within numerical constants. So now we have kind of two views of Bose-Einstein condensation. In the last video, what we did is we tried to find the temperature at which we could ignore the chemical potential, and then we could approximate, we could come up with a simpler approximation of the number of particles in excited states. And we assume that at that temperature, the total number of particles in the system was approximately equal to the number of particles in excited states. And we use that condition to come up with this definition of the critical temperature for Bose-Einstein condensation. Now, in the view from today, what we imagined is comparing the spatial extent of a particle's wave function to the space available in the system per particle. And when those two become equal, the wave functions of neighboring particles begin to overlap, and then we have this effective macroscopic wave function that occupies the entire system. And the two different views kind of lead to very similar results for these transition temperatures. Okay, good. I think actually I'm going to stop here and just have a short video because the next thing I want to talk about is kind of a new topic, and that might be best left for a new video. All right, thank you very much.